So in this problem, we discussed the issue of monotone functions. Monotone functions, they enjoy some very interesting properties, okay? And this is one of them, that if a monotone function has a limit, in fact, at certain points, then the limit is exactly the value of the function, and therefore what? The function f is continuous, okay? So, but in order to prove this, what we are going to do is something very interesting. So, first of all, note that f of x, f is monotone increasing, if it is monotone increasing, if and only if minus f is monotone decreasing. And therefore, without loss of generality, we assume f of x is monotone increasing. Okay, great. So, what does that mean? It means that if x is less or equal than y, then f of x is less or equal than f of y. Okay, for every x and y in the domain. What's interesting here is that what we are going to show, so we assume we said f, we assume it doesn't matter 0, 1, but it's just for the sake of, you could see that the interval 0, 1 does not play any role. So let's take now f, which is defined on 0, 1 into r. Okay, as we said, monotone increasing, and take x0 in the take x0 as an interior point. Okay, keep in mind that if you take 0, then you will only have the right limit. If you take 1, it will be only the left limit. So even in the case of 0 and 1, we have some very interesting properties. So what we are going to show, in fact, is that the limit of f of x when x goes to x0 plus, and limit of f of x when x goes to x0 minus exist. So remember, these are the left limit and the right limit. Okay, so we'll show that they do exist first. So let us do that because it gives us a very interesting, especially later on in a different problem where we show that the point of discontinuity of monotone functions is countable, a very fundamental property for the Riemann integration. But in any case, so let's just build it piece by piece. Huh? So here, what do we know? So we want to prove. So let epsilon be positive. Okay. So before, in fact, before even we start proving, we need to have an idea about what? About what is the limit, in fact. So your function is increasing. So I'm assuming that, for example, that it is discontinuous. So this is your x0. So what happened is, what we'll do is we'll look at the supremum of the function f of x when x is less than x0. So we'll call that. So you see, that will be the our limit from the left. And if you look at the from the right part, this one here is the infimum of f of x when x is, so set, let's call them little m, which is the supremum of f of x when x is less than x0. Okay, and capital M is the infimum of f of x when x0 is less than x. So I'm claiming, in fact, that this one is the limit of f of x when x goes to x0 minus from the left, and this one is the limit of f of x when x goes to x0 from the right. So let us prove this. Huh? This is our claim. So I'm just going to prove one of them. and leave the other one for you to do. So let us prove the little m. So let epsilon be positive. Yeah. And since the small m is a sup, then there exists, by definition of the sup, there exists x1 less than x0 such that f of x1 is going to be is it less or equal than m, of course, by definition, and greater than m minus epsilon. Okay? So in this case, we set delta to be x0 minus x1, and if you want, you can put over 2 just to make sure. Okay? But we don't need. We just need x0 minus x1. x0 is bigger than x1, so I'm putting epsilon value, but I don't need that. That's definitely x0 minus x1 over 2. Okay? So now, let's take x between the two. So let x be such that x is between x0 and x0 minus delta. Clearly, we have x1, which is less than x0 minus delta. Okay? By definition of delta. So in this case, we use the fact that f, since f of x is monotone increasing, we get f of x1 less or equal than f of x, here less or equal than m. But since f of x1 is bigger than m minus delta, we get that m minus delta, m minus epsilon, okay, is less than f of x, less or equal than m, which implies that f of x minus m is less than epsilon. Since x was taken between x0 and x minus 0, so what did we prove? For every epsilon, there exists delta. This is what we proved. I'm just putting the stuff together, okay? Such that for any x, such that x is between x0 minus delta, we have f of x minus m is less than epsilon. And that's exactly the definition of the right limit at x0. So again, what did we prove? We proved that the right limit, I'm sorry, not the right limit, the left limit, the left limit exists and is equal to m. And we have the same with the right limit. It exists and is equal to capital M. Okay? Great. So now what we want to prove is that the next claim, first, is that if f of x is monotone, we have a left limit and right limit at every point. Okay? Great. So now what we want to show is, in fact, m, the left limit. So let me just write. We claim the following, that f of x is between the left limit, I'm sorry, f of x0, when when x goes to x0, and less than limit of f of x to the right. So, in other words, the left limit and the right limit, they will squeeze the value of the function at x0. So we just need to go back to m. So what was m? We said m is the sup of f of x when x is less than x0, and capital M, which is the right limit, is equal to the infimum of f of x when x0 is less than x. So you see, if you have this, then we know by monotonicity and the fact that f of x is increasing that you are going to have f of x less than f of x0. And if you have this, then you are going to have f of x0, which is, sorry, this should be, yeah. So this will be f of x. So you see, when you take the sup of f of x less than f of x0, this will tell you that m, so the first one, this one, will imply that f of x is less than f of x0, while this one will imply that f of x0 is less than the infimum, okay, of f of x, which means what we wanted to claim, what we claimed, that the left limit is less than f of x0 and the right limit is bigger. So what happened now if you have a limit? Okay, so if limit of f of x when x goes to x0 exists, then in this case we have the left limit is equal to the right limit, okay, equals to that limit, which implies that because f of x is squeezed between the two of them, that in fact the limit of f of x when x goes to x0 is exactly x0, okay? So if you do have a limit, the limit is exactly the value, which means that the function will be continuous at that x0. Whenever you have a limit, the function will be continuous at that point, okay?